All right, 8.4, section 8.4, Foundations Math 20. We're talking about scale factors and areas of 2D shapes. So I've got, on the side here, I've got area formulas for a bunch of different shapes. You should know all these. You might not know the parallelogram and trapezoid. Not really sure. You don't use those much, but the parallelogram is just like a rectangle that's been pushed over a little bit. And I won't go through the details here, but really it's just base times height. It's very similar to a rectangle, length times width. This can also be seen as base times height, right? So if you have a parallelogram, it's just like a rectangle that's been pushed over. So it kind of looks like this, right? Pushed over, the angles are still the same. And so if that's the case, if this is still the same as the first rectangle, what you're missing is this, and what you've added is the same thing. So base times height of a parallelogram is the same as length times width of a rectangle. It's the exact same. So trapezoid, again, I won't go through this, but trapezoid is kind of 1/2 the A plus B, so you add the top and the bottom, and 1/2 of that times the height. So 1/2 A plus B times H, or it doesn't matter the order of multiplication. All right, so what I want to do is I want to test, okay, scale factor, and areas. We're going to do some examples. All right, so example 1, we're going to do two similar triangles. Okay, so let's do two similar triangles. Here's triangle number 1. And I'm going to copy this and make triangle number 2 a little bit bigger. Okay? So I am going to state that this is 10 units and this is 20 units. And the height here is going to be, let's say this is 8. Okay? So what do you think the height of this one should be? Okay, 16, right. It's a corresponding part, okay? So this is the same part, the height of the triangle with 10 as the base. This is the line emanating from the base of 10 going up to the vertex opposite. So yes, this is 16. If this is times 2 to get this one, then this is times 2 to get this one. Okay, no problem. So what do we have as a scale factor here? Scale factor is, if this is original, and this is the diagram, yeah, it's getting bigger, so scale factor is 2. We good with that? Yeah. All right, now let's test what the areas are. Okay, so area 1 is our original. So area 1 is 1/2 the base times the height, right? Or 40. Okay, here's the big deal now. Do you think that the area of this one is going to be 80? No. It might be a reasonable guess, but let's check, because there is something. There are games afoot here. Okay, area 2. Okay, 1/2 the base, 20, times the height of 16. So that is 160? Yeah. Ah, that is 160. So when we double the dimensions of a 2D shape, the areas are not doubled. Okay? In this case, this area 1, was multiplied by what to get this one? And it is a multiplication factor. We're multiplying by 4 here, right? Okay, so now consider the scale factor and the area factor. Okay, they're not the same. One is 2, one is 4. With me? Yeah. Okay, let's do another one. I'm now going to erase all of this beautiful work. No. Oh, goodness. Sorry, does Mona have it? No, she doesn't. Okay, you're not, okay, I'm going too fast. Okay, I will not erase all this beautiful work just yet. But let's take another one. Let's do the circle. Okay, I'll make some space. I'll do it down here. Okay, circle. So I have circle 1. I'm gonna let the technology make me a nice little circle there. How's that? Look pretty good for you guys? Awesome. I'm gonna copy that and paste that, and then I'm gonna make this one pretty big. But I'm gonna make, oh, come on. I'm going to flip things around a little bit, and I'm going to make this one. Hello. Hey. Computer. Obey. All right. I'm going to make this one the original. Okay. All right. So this radius here is going to be What's the number? Give me a number.
5.
9, 5, 9. Okay, this one is going to be,
3.
nah, too easy. Too easy. This one's going to be 4.5. I like it, 4.5. Okay, all right. Now, the scale factor, it's too easy. Let's do a scale factor that's not like a regular round number. Right? It's like a decimal, okay? This will make it good. All right, so what's the scale factor here? 9 times what gives me 4.5? Oh, that is way too easy. That's another easy one. Give me a break. Oh, you tricked me. Shoot the duck. Okay, no, not 4.5.
5.7.
Thank you. 5.7. Sure. Not easy. Too easy. What?
When you said thank you sound like Barry B. Benson.
Thank you. Okay. Sound like a bee?
Yeah.
From the Bee movie?
From the B movie. Like not one that
I don't see it. Okay, what's the scale factor? Well, it's 5.7 divided by 9, isn't it? That's what we have to multiply by to get this one. So it's diagram over original. So this is going to be a wonderfully complex decimal, not like 3 or 0.25. It's going to be something crazy. 5. One guy says it and everyone just repeats what that guy says. It's different.
Yeah.
Okay. 0.63. Okay. 0.633. Okay. 3 decimal places. Let's go 3. Fine. This is scale factor now. Scale factor 0.633. Okay. Let's find out what the area is. So area 1 here of our original is going to be, it's pi times r squared, right? So pi times 81, 9 squared. What is 81 pi as a decimal? 200 and some?
254.46.
Thank you. 254.469. 254.469. We'll go 3 decimal places. That's good. Okay, area 2 is the little guy here. So area 2 equals pi times 5.7 squared. All right, and that one, 5.7 squared times pi. 102.070. Okay, 102.070. 102.070. I'm trying to do 3 decimal places now because AP calculus requires 3 decimal places. So I'm going to try and model that a little bit more. I usually have done 2 decimal places, round it to 2 decimal places. Well, guess what? On the AP exam, you can take 3 decimal places and you don't have to worry about rounding it at all. You can just write that number, whatever it is, doesn't matter what's behind it. So I kind of like that. It's a little less thinking. So we'll try and go 3 decimal places sometimes to get you used to that. All right, so the question is now, what is the ratio between this and this? Does it look like half? No, not quite. Well, let's see what we got here. So what's 102? Oh my goodness. So 102, I'll just use that decimal, divided by 254.469, and there's a couple zeros. Okay, what is that? 0.40111. Okay, so area 1 times 0.40111 equals area 2. So kind of like the area factor here, right? The area factor is this one right here. So how are these two related? What do you think? Remember, we have 2 examples. We have 4 and 2 for a double, and now we have 0.4 and 0.6 for a reduction. So what could be the relationship between 4 and 2 over here? Okay, times 2 or squared. Okay, so 0.6 times 2, does that give us this one? No, what about 0.6 squared? 60% of 60%? It's going to be pretty close to 40%. Isn't it? Oh, okay, well, let's just check it out. So 0.633 squared is, look at that, 0.401. And if I took all the decimals, guess what, it'd be exact. All right, so the relationship between scale factor and area, how do they relate? Okay, You ready to write this one down? I need some more space here. Not ready for that example just quite yet. Let's go back to 100%. Okay. Okay, how are we going to write this? The area of a model of a similar shape, which is what we've been working with, is, how are we going to write this? Scale factor squared? Scale factor, oh my goodness, to the power of 2. So the area of the model of a similar shape, so the diagram or the model, is the scale factor squared. That looks very odd. But whatever the scale factor is, you just square it. So area 1 times scale factor squared equals area 2. All right? Or another way to write that is the ratio of the areas, right? So if we go area 2 over area 1 is the scale factor squared. And this is the diagram, right? Or the model. And this is the original. So we can always keep diagram and original. If we do the areas, the ratio is scale factor squared. Because remember, the dimension of shape 1 divided by dimension of shape 2 is scale factor, right? If this is the diagram and this is the original. So if we have just dimensions, that's the scale factor. If we have areas, that's the scale factor squared. And you know what's really cool is that area always is written in squared units, so it's easy to remember. Isn't that cool? That's like teacher cool. Cool. Dimensions, there's no squared units on dimensions, so there's no squared units. It's just like just straight right there. But area, squared. I'm curious, I don't know what you guys would think. What do you think this would be? Volume 2 over volume 1.
Scale factor cubed.
Oh my goodness. You might have just upset the space-time continuum. The universe may be exploding on the far end right now, and we might all be dead in an hour. Yeah, so that might be coming. Let me see. That actually might be coming. Oh, in the next section. Boom. You're done the next section too. Okay. No need for my explanation for the next section. Okay, you guys got it. All right, let's see what we can do here. Let's do an example and just see if you guys are picking up what I'm putting down here. Jasmine, do we have a Jasmine in the room? Jasmine? Happy birthday, by the way. Happy birthday, Jasmine. Congratulations. How many birthdays have you had this year?
Like all day.
Like 50?
He said all day.
All day? Like all day. Okay. Doesn't really make any sense, but I'm with you. All right. So Jasmine is making a kite from we talked just briefly about scale, not scale factor, but scale at the end of last lesson. It wasn't in the video, but scale, when you're written like this, okay, scale does not have to be the same units, really. You can have 2 centimeters is to 25 millimeters or something if you want. These don't have to be the same units when they're written side by side. Scale factor, though, does have to be in the same units, and that's like a ratio. Okay, so there is a bit of a difference there. These have to be the same units. Scale does not have to necessarily. Now, if it doesn't give you any units, that means they are the same units. Okay? So, Jasmine's making a kite from a 2 to 25 scale diagram. The area of the scale diagram is 20 centimeters. How much fabric will she need for her kite? Okay, the scale of the diagram. So, we've got 2 to 25. That's going to be diagram to original. Does that look right? So this is the scale factor. Okay? Now, that's going to have to equal, when we're talking about the ratio of areas, okay, the diagram is 20 centimeters. So which is the diagram, top or bottom? top. So this is 20, and I want to find out what this is right here. Okay. Now, is it that simple? Do I just is it this all it is? Or is there something that else has to happen here?
20 squared.
Yeah, it's meters square.
What's the area?
Okay, so this area is squared. So, okay, so we do need a squared in here somewhere, I guess, right? Because the ratio of the areas is squared compared to the ratio of the scale factors. So you want to square 20?
Wait.
Do we want to square the whole side? Do we want to do something different? What do you guys think? Okay, scale factor, right? This is scale factor. It's the ratio of areas, or of dimension to dimension. This is, right now what we've set up, this is the area factor. Okay, it's not a real thing, but I just made that up, but area factor. So what did we just talk about? Where's the relationship here?
SF squared.
It's the area factor, or the ratio of the areas has to be the square of the scale factors. So does it make sense that we got to do squared over here?
Yeah.
What do you think? Okay, pause. All right, so the scale factor, whatever it is, there's a bit of a discrepancy here whether the scale factor is actually 2 over 25 or 25 over 2. We'll maybe come back to that. This is actually not necessary. But whatever you have 2 over 25, okay, if this is original or diagram, this should be diagram. And the diagram here is the 20, this is area. So yes, you do have to square the scale factor. So this is going to be 4 over, what's that, 625 is 25 squared? Is 20 over x. So we're going to solve for x now, cross multiply, divide. Okay, you're going to have x equals 625 times 20, that's going to come up there, and the 4 is going to go down there, divided by 4. So your x should be, let's just see what happens here.
They did that.
Yeah, that's the way that's their second method in the book there, that's the way they did it.
But is it a 1 about
625
this one's reduction?
times 20 divided by 4. So I get x as 3125 here. Did you guys get that too? So 20 is the diagram, so 3125 is the actual kite. Does this make sense? Well, the ratio here, let's do this ratio here. 2 over 25, let's just check it. So 2 divided by 25, that's going to be 0.08. And then if I square that, I should get 20 over 3125. Let's just see. 20 divided by 3125. Just to check now, we're just checking. 0.0064. Look at that. I have 2 decimal places. When I multiply it by itself, I should have 4 decimal places. And 8 squared is 64, so this is true. So she will need 3,125 square centimeters of fabric. All right. So again, I know I don't know where with scale factor. I really don't understand actually why they said the scale factor was 25 over 2. It doesn't matter because we don't need to know the scale factor. We just need to know how to arrange our equation here. Okay. Good. All right. Let's just let's read the summary here. If 2D shapes, so that is just flat shapes, we're not talking about 3-dimensional here. If 2D shapes are similar, remember same shape, just different sizes, their dimensions are related by a scale factor, which is k, fine, we'll just call it k. Then the relationship between the area of the similar shape and the area of the original can be expressed as area of the similar 2D shape is area of the original shape times the scale factor squared, which is just a little different way of writing what we did before, right? Area 1, that's original, times SF squared is area 2. The ratios here, okay, so another thing you could do, right? Scale factor squared, which is what we did, is the area of the diagram over area of original. Okay, is it all fitting together?
I think so.
Now, you could rearrange this to all sorts of different things. The scale factor is the square root of the area 1 over area 2, right? Do that. You could isolate for the area of the original. So area of original is area of diagram divided by scale factor square, see? So you could take this and you could rearrange it all sorts of different ways. Does that make sense? You picking that up? Okay, so you'll have questions where, hey, what's the area of the original diagram given the ratio of areas is blah blah blah, and that's this one. So you could do that. Okay, let's do number 1, the first question in your assignment. Let's tackle question number 1. So 2 similar rectangles shown here on the right. Determine the scale factor, first of all, that produced the enlargement from rectangle A to B. Determine the areas of A and B. How many rectangles congruent to rectangle A would fit in rectangle B? That's just basically what's the ratio of their areas, I guess, right? How many would fit inside? So area 1 divided by area 2. So let's go ahead. 1A, determine the scale factor. I'm going to see if I can identify corresponding parts of these 2 diagrams. It looks like I have a height here, or this width, and it looks like I have a width here. That's all you need. Corresponding parts of similar diagrams. So 2 and 8. You see that? So we've got the scale factor is 8 over 2 or 4. Does that make sense? So 2 times 4 is 8. That means that 6 times 4, this should be 24 down here. And that's actually going to be pretty important because B asks us to find the areas. Okay, I'm sorry, I don't want to go too fast, but I'm just cooking here. Just cooking. Okay, so 2 times 6, area A is 12 centimeters squared. 2 times 6. Area B is going to be 24 times 8. Right? So 24 times 8. So what's that going to be? 20 days, 160, 4 is 32, 192? 192 centimeters squared. Does that look good? Okay. How many rectangles congruent to rectangle A would fit in rectangle B? Okay. So basically they're asking us for area B divided by area A. Right? The big area divided by the small area. That's going to be 192 divided by 12. Oh, 16, really? That's convenient. I was going to guess that. Why? Because the scale factor is 4. So the ratio of the areas should be 4 squared. You good with that? So everything should be fitting together here. This is just, again, another example of, hey, what's the scale factor? Find the 2 areas, divide the areas. Notice that the answer is the square of the scale factor. Okay. Any questions there?
That was easy.